Good afternoon. Okay, we'll have the last lecture of this ICM. Please turn off your cell phone or turn it to silent mode, please. I'm Myung-Han Kim, the president of Korean Math Society, and to my pleasure and honor, I was asked to chair this special invited lecture by Professor Yitang Zhang. Let me introduce today's speaker, Professor Yitang Zhang of University of New Hampshire. Professor Yitang Zhang received his bachelor's degree in mathematics in 1982 and master's degree in 1985 at Beijing University. He then went to Purdue University and obtained his PhD degree in mathematics in December 1991. Professor Yitang Zhang has been a lecturer at the University of New Hampshire since 1999, but in 2013, he stunned the mathematical world by an article establishing the first finite bound on gaps between prime numbers and resolving a weak form of the twin prime conjecture. This discovery, previously believed to be unattainable by current method, received wide attention and lifted Professor Zhang to an overnight public fame. Professor Yitang Zhang has been awarded the 2013 Ostrowski Prize, the 2014 Frank Nelson Cole Prize, to name a few. Now he is a full professor of the University of New Hampshire. The title of today's talk is Small Gaps Between Primes and Primes in Arithmetic Progression to Large Moduli. Please welcome Professor Yitang Zhang.
Hello. Okay, can you hear me? Okay, good. Yeah, I'm going to talk about some basic ideas toward the twin prime conjecture. But here, just like lots of problems in number theory, I would like to start with something that generalizes the problem. Then, as some special case and some partial result, we can get the bounded gaps between primes. So we start with let H be a set, H be a set of so this is a set of the non-negative integers. Our question is, we said question 1. Does there exist infinitely many integer n such that we say this is the formula 1. These numbers n plus h1, n plus h2, until n plus hk are all primes so we see that if let's look at a special case, if H just consists of two numbers, one is 0, another is 2, then we say that just means n is a prime. Meanwhile, n plus 2 is also a prime. that if this is true for infinitely many n, that is the twin prime conjecture. So just like this. But we can see that this is not always true for any set H like this. For example, if we take H is the set of 0 and 1, then how can we say there are infinitely many n? N is a prime, n plus 1 is also a prime. That's impossible because n and n plus 1, one of which is an even number. If n is large, it cannot be a prime. So like this. We say this set is admissible, just means for every prime P, there exists an integer H and such that the product I from K to H is coprime to P. This is the definition. For example, we can verify that H is 0.2 or maybe 0.26 something. We can it is directly to verify that these sets are admissible. Then there exists a conjecture H is admissible if and only if. I just erased the question 1, does there infinitely many n such that each of the n plus h1, they are all primes? The answer to question 1 is true. This conjecture usually is called the Hardy-Lidward conjecture. For the history, I don't know so much about that. Now, our approach to the twin prime is like this. Let me just recall something like this. We say the question 2. Though there exist infinitely many integers n such that at least 2 of these k numbers are primes. This, of course, the question 2 is weaker than the question 1. But if we can answer the question 2, we say yes. Then we already have proved the bounded gaps between primes. Because the set H here is given, it is fixed. At least 2 of these are primes, then the gap is bounded. So like the answer is, we say the answer is yes, if H is admissible and the size of H is large, K is large. This is the answer. Now let's see how can we approach this question. And also I would like to mention that by the by the recent result of Maynard, now it is not only for at least 2, we say at least 3, at least 4. Also, it is correct. At least 4 of them are primes. This is, I will mention how the Maynard made this approach, this different approach to this one. From now on, we are given a set H which is admissible, and the size K is a large number which is fixed. Then we always assume X approaching infinity. And we use this symbol, n is similar to x, just means n is between x and 2x. Could be equal, that doesn't matter. Then we try to formulate the problem to see this will become to evaluating and estimating certain sums. Then how can we do that? We introduce the characteristic function of the prime. Theta n, it is either equal to 1 if n is a prime. Otherwise, it is equal to 0 if n is not a prime. Now we just need to claim one thing. There exists one n which is greater than x or equal to x. For any large x, always we can find a n which is greater than x such that let's look at this one. I from 1 to k. Let's look at this inequality. We know this, the left-hand side always takes the integer values. So we say it is greater than 0, means it is greater than or equal to 1. Then we have the minus 1, so the sum is greater than or equal to 2. But the sum over the values of the characteristic function of the primes, the sum is at least is 2, just means at least 2 of the n plus h1, n plus h2, something like this. Are primes. So this implies we say at least 2 of just formula 1, I give it here, are primes. Now, how can we prove there exists an integer n such that the inequality is true? Then the approach is like this. We just choose. Choose a function, f of n. This function has no any constraint. It could be very arbitrary. But only one condition is it is non-negative. And we just like this. Let's look at this formula 2. We say this sum is first is over n, which is similar to x. Inside we have this factor. And if this sum is strictly positive, then at least one term is positive. Then for this term is positive because f of n is non-negative, but here must be positive. That just means for this n, this one is positive, as we claimed. So now we are facing such a problem. In analytic number theory, in particular, like the sieve methods problem, we are reduced to evaluate a certain sum. This sum could be very flexible. We need to choose the function f of n. But how to choose the f of n so that this is positive? We have two aspects. But here, let me say, following the way like the Serber's sieve, something like this. We say that how can we choose the function f of n? I say it's easier. Only constraint is it is non-negative. But if in order that it works, there are certain ways to do it. So we say choosing f of n. The first, it was by the Goldstone, Pins, and Yoderim. They found a form of fn. First, the f of n, in order it is non-negative, it takes the form as a square of another real function. So it is non-negative. And they choose this number n as such a form like this is somehow complicated, but they take this form. And also I would like to mention the Maynard found another form of the f of n, which is also the square of another function. But now the base of the square numbered n in Maynard's choice, it is very complicated. It is a multiple sum. Anyway, we just say something like this. And here, but I didn't explain something like this. First, L is a positive integer. Usually, we can choose it depending on k. K is the size of the, of the h. And here, the p of n, actually, it is just a product of these k numbers. So this is the k. Sorry, I couldn't. It is k on the top of that one. And the mu of d is a Mobius function. I'm not going to say something more like this. And here the b is a constant. Usually it is taken between 0 and 1/2. Okay, just like this. Then, in this way, they found that, the sum S could be written as such a form, which is t, x plus an arrow function, arrow term. We know because the f of n itself takes the square form, so after square out, we rearrange the terms. Eventually, always we get some of the major term, but also with some of the arrow term. And their method, so what we need is the main term is kx. In order that ks is positive, the first one is t must be positive. If the coefficient of the main term is not positive, we can do nothing. The second one is the arrow should be smaller. In other words, E, the arrow E is less than, we said x times a. Here the exponent is a negative a. The capital A now, it is a large constant. Usually we just take this form. Now the result before my work, the result of the Goldstone pins and Yildirim, they got is this. Here we have a B. B is a constant is a positive constant. Then the result, let me state it before mine. First, the first requirement, the main term should be positive, which is valid. Only if B is greater than 1/4. But the second one, we need to bound the arrow term. This is valid. We say the arrow is small only if B is less than 1/4 by the known Bambiri-Vinogradov theorem. So that should be a very small gap. We have two requirements. In order that the main term is positive, B should be taken greater than 1/4. Even it is slightly greater than 1/4. That's enough. But if B is greater than 1/4 for the arrow term, if we use the classical Bambiri-Vinogradov theorem directly, we are unable to bound the arrow term. That's the problem. And so here, let me just give a general form of B. The E takes the form like this, is equal to D is less than x to 2b. If B is greater than 1/4, then 2b is greater than 1/2. This value is crucial. Like this. And what I can say is, if we assume the generalized Riemann hypothesis let me say the R X CD or DC, should be DC, that doesn't matter. Is equal to the sum n is similar between x and 2x. N is congruent to C modulo D. This is the main term, subtract. Here we have something like this is the error. We need to estimate the contribution from all these errors. And the generalized Riemann hypothesis just implies that for each R, this error, it is less than or equal to up to a constant like the x, the square root of x, or maybe multiply some logarithm form. That doesn't matter. So even we assume the generalized Riemann hypothesis, still what we can get is B cannot greater than 1/4, because otherwise, if B is greater than 1/4, then we have how many terms here? At least we have the x, the square root of x terms. Each, the upper bound is the square root of x. Still, we cannot get the efficient bounded of E. Say my critical point, that is to show that we can efficiently bound the arrow E so that the second one holds for sum B greater than 1/4. In my paper, the B is just slightly greater than 1/4. B equal to 1/4 plus the reciprocal of 1168, something like this. But anyway, it is good enough. Then how can we do that? Let me say, in the history, traditionally, the estimate of the R, something like this, the capital R of XCD, we just use the Dirichlet characters. Then we transfer it into the zeros of the corresponding Dirichlet L functions that we can get the estimates. But now the recently development is very different. We do not use anything like the zeros of the L functions at all. So how can we do that? We say the first step, we impose a constraint like the D must be the dividing a product. I'm not going to repeat the S. Where here this P is the product of primes less than a small power, a small power of x. So here we just need to consider those D in this problem, we just need to say that D does not have the large prime factors. Every prime factor of D is less than a small power of X. Then the second one, originally we are going to estimate the sum of the R, X, D, C, D. But now we say it is reduced to estimating the sum of, I say this is gamma CD. Let me repeat it. Reduced the problem to estimate the sum of something like this, gamma CD. Here, gamma is supported on and 2x. And this delta gamma CD is very similar, equal to n is conjugated to C modulo D. Minus and in our argument, here, this step, we used an identity due to His-Brown. But now we select from all the possible representation of the, of the prime, the function, the calculated function of the prime. We select something very stable. Totally, we have 3 types of the gamma. Then the third one, it is a very elementary step to do it, but we can use that if D dividing, we say this P. So each prime factor of D is small, but D itself is not small. D maybe is greater than almost greater than the square root of X. Minus epsilon, something like this. Then we can make factorization. D itself is not small, but every prime factor of D is small. So D has many prime factors. D can make this factorization, written as QR. Then the range for R can be very flexibly chosen. So like this. Then the next. We say the first 2 types. Gamma is like a directly convolution of 2 functions. And usually we may assume that the support of beta is smaller than the support of alpha. That doesn't matter. So, we say beta is supported on the interval, say, from capital N to capital N. And whenever n is slightly greater than this power of x, this just means in the logarithmic scale, so slightly greater than this power of x, we can reduce the two estimated sum like this. One is q, is similar to capital Q, and R is similar to capital R. Then this is for some C. I didn't explain this, but this just means something like this. Times the delta gamma C QR. Just like this. That becomes a multiple sum. But whenever we have more and more variables, we can make certain cancellation. It is possible. So we know that because just here is just the D equal to QR, so we have two variables. Now this is similar to R. Now we say the capital R, we can choose it very flexibly. Then that is, we choose R slightly less than the capital N, also in the logarithmic scale, slightly. Then we may hold the estimate into, we use with the Closman. To reduce it into the Closman sums, then using the with bound, we can bound these terms. Eventually we get like the formula 2, something like this, get the efficient bounded. Then we just mention it. The last one. The third type. Gamma is of the form like a very arbitrary function alpha. Then we have 3 star, the convolution, beta 1, beta 2, star, beta 3. These 3 betas, beta 1, beta 2, beta 3, are just characteristic function of certain intervals. Then eventually in this way, also we need the factorization of the moduli D equal to Q times R applied to this one. And we use the Delign's theorem to get an efficiently upper bound of this type. Eventually, everything is done. So, as we mentioned at the very beginning, in my approach, the major problem is the arrow term. We need, using the form of the Goldstone, pincer, and Yildirim, we need to take the forms, take the B greater than 1/4. Even it is slightly greater than 1/4, that's enough. But now, the reduced problem on the arrow terms, we know even if the generalized Riemann hypothesis directly does not help to handle these arrow terms. But now we just reduced it into using the combinatorial arguments of the primes due to Hirschsprung. I select the 3 types. Then in certain types, using the factorization of the modular D equal to QR, the range for the R we can very flexibly choose. In each type, either it is reduced to the Closman sums upper bound. The last one reduced it is a multiple Kloosterman sum corresponding to the two-dimensional variety in algebraic geometry. Eventually, we handle all of these. Therefore, eventually we achieved the bounded gaps. Let me just stop here. Sorry about this. Sorry, really sorry.
Okay, thank you. I want to also say sorry for this technical difficulty, but I think we just witnessed that even this cutting-edge modern technology is not enough to contain great mathematics. Okay, any questions or comments? We have some minutes, so. Do you have a microphone outside? Or someone is, so questions or comments on it? Okay, seems that there's no, okay.
I think your original paper uses some different function other than indicator function of the prime numbers. Does that make significant difference in the arguments?
Of course, my approach on my paper, something, even the notation, something, are quite different from this talk. But essentially, they are the same. No big difference.
So no difference means that just the different choice of f, you
Right.
mean? Okay.
Other questions? If not, let's give a big hand to Professor Zhang and his nice talk.